How to evaluate a power tower and its convergence are discussed in this video using the example of infinitely repeated exponentiation or power tower, also referred to as tetration, with a base of pi over e and with a left exponent 2, which indicates that aside from the outer infinite power tower, we have an inner finite power tower or tetration and that keeps repeating itself. As you can see, it is keep showing up. So how do we evaluate this? Does it converge? Let's start with this inner power tower, which is just basically a left exponent 2. So we have a left exponent, which I'm going to just show what it means. And we also have our infinitely repeated right exponent. Okay, so the left exponent has another name, which is also tetration or hyper 4 operation. So tetration. And what is the meaning of this left exponent? So it means that just raise pi over e to the power itself to the power pi over e and just keep it at twice, and that's the meaning of pi over e tetrated to 2. So it just means that raise pi over e to the power pi over e, and that's it, because we are supposed to repeat this twice, instructed by 2. Now in the exponent, in the right exponent, you can see that this is repeating itself. So 1 minus, again another time, pi over e tetrated to 2. So we have pi over e to the power pi over e, and then 1 minus, keep doing this, pi over e to the power pi over e, and so on and so forth. And this goes up to infinity. Okay, just bear in mind that another way to indicate pi over e to the power pi over e or pi over e tetrated to 2 is using the tetration notation, which is this notation. So if you see this, or if you see hyper 4 notation, which is this one, exactly means the same thing, the meaning of left exponent. Okay, so how do we solve this? Does it converge? Let's make the assumption that this thing is supposed to be equal to a finite value x. I'm supposed to find x. The first thing I notice is, or we notice, is in the exponent, you can see that x keeps repeating itself, because if this whole thing is x and it goes up to infinity, then it keeps showing up again in the exponent of the base, in the first exponent. So effectively, I can write this whole thing in the form of pi over e to the power pi over e, and then 1 minus x equal to x. I need to solve this, which is not easy, but maybe the best way to solve this is just graphical way. I mean, to illustrate what is going on, I'm just plotting two things. One, I'm defining a function y pi over e to the power pi over e 1 minus x, which is basically the left hand side of equation, and I'm just taking this one and defining in another function z equal to x, which is just a straight line, as the right hand side of equation. And I want just to see whether these two curves cross each other, and whether, if that happens, it's a crossing at one point or more. So let's evaluate that. So what I did is I did the plotting in MATLAB. So I used MATLAB and I plotted. Here is the original version, the version that is not zoomed in. I just want to highlight that if you look at the x-axis, that is the value of x. So as x is varying from 0 to 5, just to showcase, this is x. And the y-axis is the value of y and z. So the y one, which is a curve that is in red color, so I'm going to highlight this in red. Okay, so that's the red color you see here. So the red color is this equation. So for that, y-axis is the value of y. For instance, when x is 0, the exponent becomes 1 minus 0, which is 1. Then the y becomes pi over e to the power pi over e, which is exactly this value. So pi over e to the power pi over e is equal to approximately equal to 1.1821, roughly. So that's exactly what this point is indicating. It's above 1 below 1.5. Okay, so that's the crossing. Now you can see that The as expected z equal to x is monotonically increasing, just a line with a tangent of 1 as expected. And the red curve is monotonically decreasing. So these monotonically increasing, decreasing, let's say functions or curves, they only cross each other at one point, which is exactly when x is equal to 1. And interestingly, the outcome is also 1. It's obvious when x is 1, z is 1. When x is 1 here, exponent becomes 0, and pi over e to the power pi over e to the power 0 becomes 1. So if you set x equal to 0, y is 1. So interesting, when x is equal to 1, then left hand side and right hand side become, they both become 1. So look, based on this proof, the equation has a unique solution, and that unique solution is x equal to 1, and the outcome of that is here is 1. So basically this combined finite tetration and infinite tetration, it has a unique solution, and that solution is just 1. So the answer to this is just 1. And for a zoom in version of this, just in case it helps with better seeing, I have a zoomed in version of this plot as well here. So if I focus, basically, if I focus zooming into this range, then this is what I see. And you can see that as x is equal to 1, now we are getting to 1, and of course the red curve, the red plot, as expected, when x is equal to 0, then it gets to 1.1821 as expected. Alright, I hope that this example is helpful in terms of showing how potentially we can deal with combined tetration or compound tetration problems in which we need to take care of an infinite and a finite tetration as an example and evaluate whether it converges. In this case it does, as the plot showed, or not, and how to check whether the solution is unique or not, because there is a chance that there are examples in which the tetration converges to a value, but then the value is not unique. For example, possibility that the two plots or two curves, because they are not monotonic, they might actually cross each other at more than one point. Hence, there is not a unique solution for the problem. So we need to be careful about that. In this example, we are not worried about that situation because of the monotonic behavior of the two sides of the equation. Okay, thanks for watching. I hope this is helpful.